I'm going to redo the 4.6 practice 1 lecture. I'm breaking 4.6, which is our linearization section, linearization and differentials. I'm going to break that up into 3 separate assignments, make them kind of shorter. Okay, you guys are probably ready for some shorter assignments after those optimization monsters. So we'll just cover this a little bit today. I'm going to try to keep this short. Obviously, I'm out in cyberspace for you right now, and you're kind of working on your own on this stuff. But hopefully this will leave you a little time to maybe jump in and work on the assignment as well. All right, so we talked a little bit about this last time, but let's go back to square one. So linearization, the whole concept of linearization or linear approximations, this is stuff that we already really know about, and we've already seen these concepts before. So the idea is that if we've got some curve, some function f, then that's differentiable at x equals a, so it's continuous and there's no sharp corners. The idea is that for in the neighborhood of a, for values of x that are close to a, this curve is approximated by a line. And so a linear approximation is a quick and easy way to approximate the values of the function in this region around a. Okay? So it would look something like this, wouldn't it? So if we draw the line that's tangent to the curve at a, you can see that the blue line and the black curve in the region around a, they look like the same thing. Okay? And we've talked quite a bit about that idea. So if we start with just our point slope form of a line, let's go back to algebra 1 here for a second. So y minus y1 equals m times x minus x1. Remember what the parameters are, the numbers that we're plugging in here. X and y are the variables. X1 and y1 are the coordinates of some point that we know, and m is the slope. Well, all of that stuff, we can get to pretty easily for our linearization, for our linear approximation. A and f of a are the coordinates of the point that we know, and we're always going to choose a is a value of x that is convenient for us. It's easy for us to evaluate the function at a. So we're going to look at an example here in a second where we're trying to approximate f of 2.1 for the function f of x equals 2 over x. So where do you think the convenient value of x would be for us to calculate? We want to pick a value that 2.1 is close to, but that is really easy to plug in. So take a second, pause the video if you need to, but just think about that. Think about what you anticipate the value would be that we should choose for a. Okay, hopefully you're thinking along the lines of something like 2. Right? I mean, 2 is close to 2.1. 2 is easy to plug in and evaluate. We get f of 2 equals 1, right? So that would be a logical choice of a for us in this upcoming example. Okay, but we're able to plug in 2 parts of our point slope equation, point slope formula. x1 is represented by a convenient value of x, and y1 is represented by f of a. Okay, what about m? Well, m is the slope of the line. That's dictated by the slope of the curve at a, isn't it? So we're going to get that from the value of the derivative at a. In other words, f prime of a. What the value of the derivative of f of x is, f prime of x, when x is equal to a. So if we make those substitutions, look what we get. Y minus f of a, there's our y1, equals m, f prime of a is our m, times the quantity x minus x1, where x1 is represented by a. And if we solve for y, we just add the f of a to both sides, we get our linearization equation, our linear approximation equation. So L of x, which sometimes, this varies from book to book, but a lot of times books will call linearization L of x. So that's the output, the y value of our tangent line is just equal to f of a plus f prime of a times x minus a. Okay? All right, so let's look at our example then. Here's the example we're going to take. F of x is 2 over x. We want to use a linearization to quickly approximate f of 2.1. So what's that look like then? Okay, well, f of x is 2 over x. So we need to do a couple things. First of all, we need to calculate, a is going to be 2. right? We picked 2 because it's convenient. So f of a becomes f of 2, f prime of a becomes f prime of 2, and x minus a becomes x minus 2. We want to evaluate our linearization at 2.1 because that's the point that we're trying to approximate, right? We want to approximate f of 2.1. So let's take the derivative. If f of x is 2 over x, that's the same thing. Now, just quick reminder, we don't want to use quotient rule to differentiate this because we don't have a quotient of functions. We just have a constant divided by x. If I've either got a constant on the top or the bottom, we avoid the quotient rule and we instead use the power rule, right? So in this case, we would just think of this as being 2x to the minus 1. And if I differentiate 2x to the minus 1, isn't that just going to give me minus 2x to the minus 2? Well, there it is. Minus 2x to the minus 2 is f prime of x. So f of 2 we already established is 1. 2 over 2 is 1. F prime of 2 is going to be negative 2 over 4, right? Negative 2 over 2 squared, so that's negative 1/2. And now we're able to plug values into our linearization and just come up with a numerical answer. So L of 2.1 is f of a, which is 1, minus f prime of a. F prime of 2 is negative 1/2 times 2.1 minus 2. Okay, so instead of multiplying by negative 1/2, we're just going to combine those terms and say minus the quantity 2.1 minus 2 over 2. And that's pretty easy to calculate, right? We can do that in our head. 2.1 minus 2 is 0.1. Half of 0.1 is 0.05. 1 minus 0.05 is 0.95. Done. That's the output of our linearization. Okay, and that's pretty close, right? That's pretty darn close. At that point right there, I mean, we're slightly off, of course, but not much. Okay, how much? Well, that's the next question. We want to know how good is our approximation. So our approximation, the way we can tell is we're just going to compare the output of the linearization to the actual output of the function, right? Is this a practical thing to do? I mean, I guess you might say not really, because if I have to calculate the actual output of the function to calculate how good the approximation is, well then why didn't I just take this number to begin with and be exactly correct? So this is, I mean, is this something you're gonna actually probably do all the time when you're using a linearization to make an approximation? No, not all the time. You just know that a lot of times we can just see here that it's a pretty good approximation in the region of 2. So we just want a quick and easy approximation so we can get a ballpark figure. A lot of times in math, to know, roughly what is f of 2.1 going to be, and so we just apply the linearization and call her quits. But here we're going to go a step further. We're going to answer the question, how good is our approximation? And so the way we calculate that, and we talked about this last time, relative error is always the same thing. It's going to be the approximate value minus the exact value divided by the exact value. It's always that way. Okay. Sometimes, like in scientific applications, you might talk about maybe you're making a measurement compared to a known quantity, for example. In that case, you'd have the measured value minus the known value divided by the known value would be calculating a relative error. So in our case, then we've got 0.95 minus the exact value of 0.9524 divided by 0.9524, and the calculator tells us that that's pretty good. That's negative 0.00252. If we want to turn that into a percent, obviously we just multiply by 100, so we move the decimal 2 places, and we just get negative 0.252%. Okay? Now, if we want to talk about an absolute relative error or an absolute percent error, then we're just going to ignore the sign and we're going to take the absolute value of that difference. Instead of, like, this is kind of nice to know that our relative error and our percent error were negative, because that's telling us that we undershot, didn't we? Right? That the relative error, the fact that it was negative means that the output of the linearization was less than the actual value. So we underestimated with our linear approximation. You lose that sign with an absolute error, but sometimes that's all we want is just a percent, just an absolute percent. Okay, I think a lot of the questions in the assignment are actually asking for absolute error. All right, so one other question. We didn't talk about this last time, but I thought this might be a good thing to throw in there. So we made this approximation of f of 2.1 using our linearization. So how could we tell without having to calculate this somewhat hokey error calculation, right? And the fact that it was negative told us that it was an underestimate. But what if we don't want to go through that whole process? Because that requires us actually evaluating the function at 2.1. And the whole point of the linear approximation is to avoid that, to make a simple approximation. How could we predict if it's an overestimate or an underestimate? Okay, I'm going to ask you here at this point, why don't you just pause the video for a second and ponder that for a moment and see if you can come up with, if there's a calculus concept, something that we've talked about that might give you an easy clue about whether your estimate is going to be an underestimate or an overestimate. Okay, maybe you thought about this, and if you did, possibly you came up with the idea of concavity, right? Concavity is very useful here. If we determine, we don't even need to know the value of the second derivative at a, we just need to know the sign of the second derivative at a. At our convenient value of x at a, if f double prime, if the second derivative is positive, think what that means. The curve is concave up, so it's bowl-shaped up, right? So that means then if it's concave up, the tangent line would have to sit below the curve, right, if it's bowl-shaped up. So in that case, we would know that our linear approximation for all values close to a would have to be underestimates because the line is below the curve, right? If the second derivative is negative, so the concavity is down, it'd be the opposite. Then we'd know it's an overestimate. And we can see that if we look at the graph we have of this function, right? Here's f of x. We could easily calculate for our function, if f of x is 2 over x, let's just do this second derivative calculation real quick, right? So we know f of x is 2x to the minus 1. So f prime of x is negative 2x to the negative 2. What's f double prime going to be? If we just apply the power rule again, we're going to get negative 2 times negative 2. That's going to be positive 4 x to the negative 3, or if we write that as a fraction, 4 over x cubed. Well, for any positive value of x, and we're looking at 2, right? We're looking at values around 2. 2 was our value of a. This is obviously going to be positive, right? So we can see right away that this is going to be bowl-shaped up, and so our linear approximation would the tangent line would sit below the curve, and so it represents underestimates. Okay. Here's where I'd probably ask you if you have questions, but I'm not here, so hopefully you don't. Okay, let's use this in a slightly different context here. Let's go ahead and this is kind of fun to do fun in a math sense, right? In a geeky math sense. If you want to impress your friends, you can do a pretty good job of estimating square roots as long as the input number is somewhat close to a perfect square. And if it's far away from a perfect square, this is pretty hard to do because it's hard to calculate square roots in your head if they're not perfect squares because they're irrational numbers. There are some little tricks you can use to do that, but it's not easy to do. So let's take something like 9.1. This is set up perfectly here because we know that square root of 9 is 3, so that's a very convenient value of our input. That's the value we should clearly choose for a, is 9. So if a is, well, what's our function going to be? I mean, this is a square root function, right? We're plugging our inputs into a square root. So f of x is just the square root of x. And so if it's a square root of x, that's the same thing as x to the 1/2. So f prime of x then is just going to be 1/2 x to the minus 1/2, or another way of saying that would just be 1/2 times the square root of x. So that's pretty easy to evaluate also then. We can evaluate that for our convenient value of 9 pretty easily. That's just 1/2 times 3. And so f prime of 9, we can easily calculate that to be 1/6. So that's all we need to make a pretty simple approximation of the square root of 9.1. Remember, L of x is equal to f of a, right? In our case, that's f of 9, right? Plus f prime of a times the quantity x minus a, okay? If we plug all that stuff in, then what are we going to get? Right? We're just going to get f of a is going to give us 3, right? Yeah, let's write it this way. I don't like that. We're skipping too many steps here. I'm going to go back. So this is going to become L of 9.1, which is the same thing as the square root of 9.1, is approximated by the square root of 9 plus 1/2 times the square root of 9 times 9.1, right? The value of x that we're inputting, which is 9.1 minus 9. So what's that give us? 3 plus 1/6 times 9.1 minus 9 is 0.1. Well, we can do that. That's not a big deal. We could say then that that is 3 plus 0.1/6 is the same as 3 plus 1/60. I could multiply top and bottom by 10. So we just get 3 and 1/60. Okay, well, what's 1/60? I mean, if we had to do this and come up with a decimal on the spot, here's the way I would do this. I would say, well, right about here, I'd say, I know what 1/6 is. 1/6 is half of 1/3, right? Half of 1/3 is 0.3 repeating. So 1/6 is equal to 0.16 repeating, okay? Times 0.1, what's that going to do? If I multiply that by 0.1, I'm just moving the decimal over one place to the left. And so this term right there ends up just being, it's going to give us 3 plus 0.016 repeating. Well, that's just 3.016 repeating. Okay. How close is that? Well, I don't know. Let's find out. Square root of 9.1. We can do that in Desmos. Is 3.016620. So that's pretty close. I mean, we're pretty close. Out to 4 decimals, we got it exactly right. And then after that, the answer deviates from what we had, but that's pretty darn close for just a shirt sleeve quick estimate. Okay, how about something like this then? It's a little tougher function. Let's try this one. So we want to make a quick estimate, something that we could, with a little practice, could even do, in our head, or maybe even just like on a lot of times in college, they call these cocktail napkin approximations, something you could just jot down on a napkin, right, and get an answer real quick. Okay, so what's the value of A going to be then? All right, we want to pick a value of A that's going to be our input value that's going to be close to 347 but convenient. Well, that would be 343. 7 cubed, is that right? 7 cubed is 343. So that would be a good value for A. Oops. So let's do this. So we've got our linearization, right? L of x is approximated by f of a plus f prime of a times x minus a. Now we just have to plug in what we know. So we're plugging in for our value of a, we're plugging in 343. And the value of x is 347. Okay, so here's what we get. L of 347 is an approximation of our function, right? Evaluated at 343, right? Our linearization is an approximation of our function at 343, plus we've got this x minus a term at the end that's going to add a little offset to that. So we got to calculate the other pieces of this then. So we know what a should be and what x is going to be. What's the function in this case? So what are we doing to our input value of 347? Well, it looks like we're taking the reciprocal of the cube root. So it's 1 over the cube root of x. That's supposed to be a cube root right there. Okay. So we could write that maybe more conveniently for doing calculus. We could write that as x to the minus 1/3. Negative because it's on the bottom. It's a 1/3 power because it's a cube root. So f prime of x then, by the power rule, we'll take the 1/3 out front and we'll subtract 1 from negative 1/3, which is negative 4/3. So f prime of x equals negative 1 over 3 times x to the 4/3. Well, what is x to the 4/3? That's a cube root of x to the 4th. Remember, the bottom tells us the kind of radical that we're using, and the top tells us what power we're taking it to. Okay? And so we can now do some evaluating. F of 343, just the cube root of 343, which is 7. F prime of 343 is equal to negative 1 over 3 times the cube root of 343, which is 7 to the 4th. So 7 to the 4th is the same as 49 squared. We could actually do this one in our heads. 49 squared is close to 50 squared. I probably shouldn't take time to do this, but think how that's going to be different from 50 squared. We know 50 squared is 2,500. Well, 49 squared, here's how I would do this. How is 49 squared different than 50 squared? 49 squared is a factor of 50 less than 49 times 50, right? So I could take 50 squared, and not a factor of, it's going to be, we're going to subtract that much. 49 squared is the same as 49, a product of 49 49s, right? 50 squared is a product of 50 50s, okay? So 50 times 50 means, I don't want to say this, gosh, this is going to probably, 50 times 50, think about what that would look like as a sum, right? That's like saying, I'm going to add 50 to itself 50 times, right? 50 plus 50 plus 50 plus, and so on. That's how we get 50 squared. 49 squared is I've got a string of 49 plus 49 plus 49 plus 49, 49 times, right? 49 times 49 is just 49 added to itself 49 times. Okay, so then how much more is this? Well, 49 49s, if I wanted to get 49 times 50, I would have to take this result and add 50 to it, right? If I wanted to get to 50, hang on a second. No, I'd add 49 to it. Sorry, I screwed that up. 49 times 50 means 50 49s. So instead of 49 49s, I'm going to add 49 to this result to get 49 times 50. to get 50 times 50, which is 50 squared, instead of 49 50s, now I've got 50 50s. And so I'm going to add 50 to that one to get 50 squared. We would just reverse that process to go from 50 squared to 49 squared. I know 50 squared is 2,500. So all I've got to do is subtract 50 once and 49 once, and I got my answer. So you can do this pretty quickly in your head. This is a good little trick. So that's going to give us 2,500 minus 49 minus 50 is the same thing as minus 99. So the answer is 2401. That took a long time to explain, but if you're interested enough to go back, and I didn't do a very good job of that either, but if you're interested enough to go back and think about that, you can do this stuff in your head pretty easily. Like if you're within like 48 squared or 49 squared or 51 squared or 52 squared, once you've done that a couple times, you can crank that out in your head pretty easily where you can come up with that answer without a whole lot of effort. And it looks pretty impressive, but it's really not that big a deal. Okay, back to the problem. So we know what f prime of 343 is. We know what f of 343 is. I guess we didn't actually finish this, did we? So this is negative 1 over 3 times 2401. Okay, so what's that going to be then? That's going to be 3 times 24 is 72. So I'm going to get negative 1 over 7203. And now I can take all this stuff and plug it into my linearization, right? So here, we'll just write these in terms of numbers right here. F of 343 was 7 plus f prime of 343 was negative 1 over 7203 times 347 minus 343 is 4. Okay, so we end up with our estimate being, our estimate here ends up being 7 minus 4 over 7203. Okay, is that right? I'm hoping so. I did all that in my head and that probably wasn't smart. I probably made a mistake, but let's check it. Okay, we're just gonna define, just to check my math here, f of x equals you know what? Our function, I did, that's supposed to be 1/7, isn't it? I see one mistake, right? F of x is 1 over the cube root of x, not the cube root of x. So you probably saw this and were laughing at me earlier here. This should have been 1 over the cube root of 343. So it's 1/7 minus 4 over 7203. Okay, so what's that give us? F of x is 1 divided by cube root of x. Okay, and we can even, this is kind of cool, maybe you don't know about this, but I can calculate, I'm going to say g of x is equal to f prime of x. That's kind of nice. And so now in Desmos, I can check this whole thing. I can say f of 343 is 1/7. There it is. And I can turn that into a fraction. There's my 1/7. G of 343 is this as a fraction. That's negative 1 over 7203. Yeah, so, okay, so we were right. We were right. Okay. And then we multiplied that by 4 because we've got to multiply by x minus a. Okay. So that gives us our approximation then. I mean, we got to turn that into a decimal, I suppose, which is kind of tough to do in your head, I suppose. So maybe this ends up being a pretty tough mental exercise at that point. But we get f of 343, whoops. Our linearization is f of 343 plus f prime of 343 times 347 minus 343, which we know is just 4. And there's our estimate, our linearization, 0.1423. Let's just see what the actual answer is. So if we do f of 347, wow, it's the same thing out to 1, 2, 3, 4, 5 decimal places. Out to 5 decimal places, we get the same, actually out to 4, because that would round up to a 1. So out to 4 decimal places, our approximation is true to the actual number, okay? Let's try one more. Last one. How about this? How long is this taking, first of all? Where are we on this thing? I guess we'll do one more. This is kind of a bonus one. This is tough. Use a linear approximation to estimate the following quantity. Choose a value to produce a small error. Okay, so I guess, what does that mean? On the assignment, this is just a question. I don't think I actually assigned this one. This is pretty tricky, but they're going to sound the same way. It says, choose a value to produce a small error. So on this last example, if you had just plugged in 1 over the cube root of 347, you would have gotten that wrong, because the right answer is the wrong answer in this case. We don't want the right answer. We want the approximate answer to 4 decimal places. And so the correct answer would have been whatever we got on our calculator. I think it was negative 0. Well, what was it? Where was that thing? Right there. It was positive, not negative. 0.1423. And on this one, it turns out that if you had just plugged in, the actual value of the function to 4 decimal places, it rounded the same thing. So you would have lucked out in this case and gotten it right. But on a lot of these, you wouldn't. Okay, so that would be our answer. Even though it's, this time you lucked out. Usually the answer that you get from the approximation is going to be off just enough that if you just put in the exact answer, it's not going to be correct. Okay, so let's try this one. So what's a convenient value close to 27 degrees? Well, that would be 30 degrees. But anytime you are mixing angles as inputs with raw angles that are outside of trig functions, you can't use degrees. You have to use radians. And if you're ever unsure, just convert everything to radians, because you can never go wrong with radians. Okay, so we would want to convert this to radians first of all. 27 degrees. Actually, we don't really want to convert 27 degrees to radians. We want to pick what's our value of A, which would be 30 degrees. And we want to figure out what is the value of, so A is 30 degrees, X is 27 degrees. We want to figure out in our linearization formula, and let's just write that down. This is going to be approximated by f of A plus f prime of A times x minus A. Well, A is 30 degrees. We don't ever really need to figure out what x is in radians. We just need to know what x minus A is in radians, right? So x minus a is equal to 3 degrees. So we need to be able to convert this into radians and that into radians, right? And so we use our conversion to get to radians. We know if we multiply by pi over 180 degrees, that's our changer. Well, we already know what we're going to get for 30 degrees, right? The degrees cancel. 30 over 180 is 1/6, so we get our, pi over 6, but we already knew that. 30 degrees corresponds to pi 6th radians. But we do need to know what this is. What's 3 degrees? 3 degrees times pi over 180 gives us, pi over 60. So that, we do need that one, pi over 60. Okay, that's what x minus a is going to be. And so now we should be able to plug a bunch of stuff in here. What's our function? Well, it looks like a cosine function. So if f of x equals cosine x, then f prime of x is just minus sine x. We know that. And so this is going to be approximated by f of 30 degrees, right? F of x is cosine x. So cosine 30, whoops, I don't want to write it as 30 though. I want to write it as pi 6. Plus f prime, so that's minus sine of a is pi 6 times x minus a. Well, x minus a is just pi over 60. This one right here, because I've got this angle that's outside of a trig function, this is the reason that we need radians. You can't have, like if I were to try to plug in 3 degrees, that doesn't make any sense. You can't multiply some expression by degrees and expect to get some meaningful answer, because degrees are arbitrary, right? We just arbitrarily chose 360 degrees in a circle. We might have chosen 3,600 or 720 or something different, and that would have changed our answer. Well, the answer shouldn't change. An absolute answer shouldn't change based on what we arbitrarily choose to measure angles in, right? But radians are not arbitrary. Radians have meaning. We know that there are always going to be 2 pi radians in a circle regardless. And so that's why we have to be in terms of radians. So what do we get for our answer then? Cosine of pi 6 on the unit circle. That's that point right there, isn't it? That's pi 6. So we're going to get big X value, so square root of 3 over 2, and small y value, so 1/2. So we're getting square root of 3 over 2 minus sine of pi 6 is 1/2 times pi over 60. So then what's that give us? It gives us square root of 3 over 2 minus pi over 120. Okay, and we would, that's a good approximation. If we want to make it a decimal, we can. As a decimal, what's that going to equal? Make sure we're in radians mode. We are. Well, actually, we don't need radians. We're just getting an answer here. So square root of 3 over 2 minus pi over 120. There's our approximate answer. What's the exact answer? Well, the exact answer would just be cosine of 27. Oops. Well, we'd have to put that in radians, wouldn't we? So we'd say cosine of 27 times pi over 180. And, it's not that close, fairly close, but not that close. I mean, we're reasonably close, but 0.84 compared to 0.89. So we're off by 0.05. Okay? All right, let's make one more glance at that and make sure I didn't make some stupid mistake that you're laughing at me about. Okay. No, I think that looks good. Okay. All right. Have at it. First assignment just is a bunch of stuff like we just talked about. So good luck. Have fun. I'll be back. And if you have questions, bring them to class on Thursday.